In this video, we will look at localization. So we'll explore three common methods used for localization. We've got the Kalman filter, we have got the Markov localization approach, and we will look at the particle filter. The particle filter is currently the most popular way for a robot to localize itself, and it's essentially a combination of the above two methods. So we'll look at each one of these in turn and see how they work. So we'll start with the Kalman filter. Consider taking two measurements, Q1 and Q2. The best estimate of our measurement is Q. So this is actually the measurement we believe it to be, and our measurements are Q1 and Q2. So what we can do is work out a difference between the measurements we've just taken and the actual measurement Q. And for each of these values we've tried, or we've measured, we can put some weighting associated with that, Wi. So if we rearrange this equation, or if we want to find the minimum of this equation, we can differentiate it. And at a minimum, then this differentiation equals 0. So we have this term equal to 0. And if we rearrange that, what we get is Q equal to this term here. So all we're saying here is the best estimate of our measurement Q is the sum of Qi multiplied by the confidence, or weight or confidence in that measurement, over the sum of all the weights. So what we have here is a weighted mean. If you imagine all the Wi's are 1, then that is simply the mean of all the measurements. By putting Wi in, then it's weighted mean. So we're taking more importance on some of the measurements compared to other ones. So the more accurate measurements, we're taking a greater account of. We can take our weight, or our confidence in the value, as the reciprocal of the variance. So we said as the scatter in our distribution of our measurements, if this distribution is wide, the variance is large, and there's a large scatter in measurements. If this value is small, there's a very small scatter of measurements, so we're more confident in the measurement. So 1 over the variance gives us an appropriate way of weighting the values. So if we've got a very narrow spread of measurements, then this weighting will be high, and therefore when we calculate our weighted mean, more weight will be put into that value. So if we go back to this equation here and put in our Wi from this equation here, then we get this term, which we can expand out and simplify into this term here. So our best estimate of our measurement Q is going to be from our measurements Q1 and Q2 times by some weighting function, which is a function of the variance, or the standard deviation squared of our measurements. What we can do is recombine or reconfigure that equation to look like that. So that looks very different to that equation here. But if you manipulate the equations around a little bit, you'll find they're totally equivalent. Now, although they are equivalent, they fundamentally, if you think about them, the mean sort of, the concept is slightly different. In this equation here, what you have is two measurements, and you're using both of these measurements to calculate a mean. In this measurement, or in this equation, what you have is one measurement, Q1, and what you're doing is correcting that measurement by taking another measurement, working out the difference between the measurements, and then doing a weighted correction factor. So as I said, they're entirely equivalent, But what that means is we don't have to, when we're running this algorithm, it doesn't mean we have to keep account of all our measurements we take. All we have to do is know what our current estimate is and then correct that current estimate with the latest measurement, Q2. So it's a way of calculating an ever-changing mean by new sets of measurements. The error in our new estimate, or the standard deviation from this correction, just comes from this formula, and it's just considering the standard deviations or the variances already present, and it's a reciprocal addition to work out what the new standard deviation is, which is this equation here. So that is the principle of the Kalman filter. Rather than take lots of measurements and work out the average of all the measurements, what it does is takes its current estimate of what the measurement is, it takes another measurement, works out the difference between these two measurements, and then uses an appropriate scaling factor to then slightly correct for this estimate to give us our new estimate. This new estimate is then taken onto the next stage, and then that is corrected for by the subsequent measurement. And the error in our new measurement is just using this formula. The error in the measurement is the error in the previous measurement changed by a correction term due to our new measurement. The scaling factor, or the weight, is a function of the various errors in the measurements taken. Now that's for the static situation. For a dynamic situation, the robot is moving. So we have to slightly modify the equation. So what we have is a position, xk. We've got a velocity of a robot, u. So we're starting at a position xk. The robot moves with velocity u for a certain time. And after that, it takes another measurement, or an independent measurement. And then it uses this independent measurement with an estimation of position from our position and our velocity to work out what we need to correct for in our estimate of position. So for the dynamic Kalman filter, it looks very similar to the static one. So there's our static Kalman filter. For the dynamic Kalman filter, we have to account for the change in position at this point here and this point here by adding a velocity multiplied by time value. So there's our initial position. We've moved at a certain velocity for a certain length of time. So we correct for position using that. So we expect to be in this position. We've taken a measurement and we found we're in this position. So we work out the difference between what we just measured and where we expect to be, take a weighting correction factor, and then we correct or update our position and store that as our new expected position. And we can accordingly scale our correction factor with the errors associated with the measurements. So we'll work through this graphically to give you an idea of how it works and brings together information from previous in the lecture. But in terms of a worked, calculated example, if you look at the exercises, there's an exercise where a train is moving along a track and doing measurements from a signpost. So you can see how, in terms of the calculation, it works out. But for this video, we'll just do it graphically, this calculation. So we're going to have a robot with wheel encoders for debt reckoning. So that's our estimate of position. And we're also going to have a laser rangefinder, and that is our our Z measurement. So that is our other measurement on trying to identify where we are. So we've got 5 stages to the procedure. So our first stage is we have a robot in this position here. There's some uncertainty in the position, so we'll start with that. Some uncertainty, it moves. Now if you remember to the lectures, if we remember back to a previous lecture, then as the robot moves, this error increases. So we're going to have a larger error after a certain time due to the errors in debt reckoning. So we've got large error associated at that point. And that is our x plus ut term. So we start at position x, we've moved with velocity u, so we're now in a new position with an associated error. So what we'll next do is use our sensor, so our laser rangefinder, and try and find features in the environment that we can help to identify exactly where we are. So we've used our laser rangefinder, we've taken these measurements, and it looks like we've identified a feature along here, which is a wall here. So we're going to do our feature extraction. We can identify various features in the environment. So if we plot our features in modal space, these are our R values and our alpha values determined from these line fits, and these are plotted here. And they're going to have some uncertainty associated with them. So slight how confident we are in this fitting of the data. Now we should have a map of the environment, so these features will be stored in the map. So what we can do is try and match the features we've just measured here with the features stored in the map. Now we know precisely where these features are in the map. However, we don't quite know where the robot is. So there's a slight error in the position of the robot. So when we transform the map from the global frame to the robot frame of reference, then because of this error in the robot position, we're going to get an error in the position of these mapped features. So these are our features in our map. When we transform to the robot frame, it's going to introduce a slight error in these features, or the location of these features. What we next have to do is try and match the features we've just measured with those that are in the map. So again, we have to account for any errors, or there won't be an exact match. So if we think about what errors are associated and try and get a match considering the errors. So we're going to have a situation like that where if you take account of the errors, then this looks like a match, this looks like a match, this looks like a match, and this is potentially a match. We will have certain features that we have measured and it's not in the map. So for example, this feature here we've measured with the laser rangefinder, but it's not in the map. So that might be, for example, a person walking past the robot. And there'll be features in the map that we haven't recognized from the sensor. So for example, this might be a glass door that is present, but we haven't measured it because it's a laser rangefinder. Didn't see it. This feature here is out of range of the laser rangefinder. So we won't be matching that one. But we've got a certain number of features we've matched. And from these matched features, we can get an estimate of the position of the robot. So by using these matched features, we've got our independent measurement Z. And what we can do is apply this measurement. We can apply this measurement we've just had of the features and combine that with our estimated position using our Kalman filter to give us an update of our position. So if we do that graphically, we've got the robot. This was our error in position. We've tried matching features and we've matched them as best we could. And this is where, with respect to the features, we think the robot is. And therefore applying the Kalman filter to this situation gives us our best estimate of the robot being in this area here. So as you can see, we've reduced the error. There's a large error due to the odometry, an error associated with matching the features, but by applying the Kalman filter, we're trying to reduce all these errors to give us our best estimate. So I was doing it graphically. As I said, if you have a look in the exercises, there's a numerical example of that, which will better illustrate how it works using the equations. Markov localization is a completely different approach compared to the Kalman filter. With this approach, the robot considers it could be at any location in the environment. The disadvantage of this approach is it's very time consuming as it involves a lot of calculations. The advantage is the robot is never truly lost. So if you consider the kidnapped robot scenario where you pick a robot up and put it down somewhere else, the Kalman filter would get confused by this and you would lose localization. With the Markov localization approach, this is not a problem. If we look at the theory behind Markov localization, we consider this equation here, which is saying that the probability of given two events A and B, the probability of event A happening and the probability of event B happening is the probability of event B multiplied by the probability of event A given that B has occurred. Similarly, we can rewrite this equation, probability of A and B occurring, by saying it's the same as the probability of A occurring multiplied by the probability of B occurring given the probability of A has occurred. So what we can do is we can match these two terms up, and this gives us Bayes' formula, which is this, which says that the probability of A occurring given that B has occurred is the probability of A occurring times by the probability of B occurring given A has occurred, or for the probability of B occurring. The probability of A, or A is our location and B is our sensor reading. So P of A is the probability of being in a certain location. PB is the probability of taking a sensor reading. Now we will be taking a sensor reading, so that is always 1 in our case. Probability of B occurring given A has occurred is the probability of taking a sensor reading in a certain location. And then this part, P/B, is the probability of being in a location given that you have just taken a certain sensor reading. So as we work through an example, this will make a little bit more sense. So we'll consider this example. You can ignore points 6 and 5 for now, as this is part of the exercise. But what we have is this scenario where a robot is moving along a corridor. It's potentially in location 1-2 or it's in location 2-3. And this is the chance it's in these locations. So it's 5 times more likely that it's in this location 1-2. We've got walls in this. This is just a blank feature. It's a wall. We've got hallways. So we're open hallways. And we've got doors. Doors can either be open or shut. We don't know whether they are open or shut. But what we do know is there's a 60% chance of a door being closed. So that is our problem statement. What we also need is a measure of what is the likelihood of taking a reading given that we're at a certain location. So this is something we need to decide before we set the robot moving. So this is what's known as Dervish's certainty matrix, and it is P of B/A. So it's a probability of taking a sensor reading given that we're at a certain position. So for example, if we're next to a wall, the probability of not detecting any feature, because it's a blank wall, is 0.7. The probability that we take a measurement and we think it's a closed door is 0.3. Alternatively, if we're next to a closed door, the chance of that measuring that as being a closed door is 0.6. although we might mistakenly think it's an open, it's a wall, in which case the probability of that happening is 0.4. So given we've got a certain scenario, a wall, a closed door, an open door, or a hallway, what is the likelihood of either taking a correct measurement or a wrong measurement in that position? And this is what this term signifies. So what we'll do for our problem is look at the robot, and we've got our starting location, and then what happens is the robot moves and it next detects, so the next detected feature is going to be an open hallway, so an open hallway on the left of it and an open door on the right. So the robot's moved, it's taken these sensor readings, it thinks that's where it's at, and what we need to do is calculate the position, or calculate the likelihood that it's at position 2 or position 4. So first we'll consider the likelihood of it being at position 2. So to be at position 2, here, we start off in this position and we move here. So the likelihood of starting in this position is 1. So we've got a 1 here. It says we've measured an open hallway on the left. We've actually got an open hallway here on the left. So given we've got an open hallway on the left and we've measured an open hallway, then it's a 0.9 chance of that happening. So we've got 0.9 in there. We've measured an open door on the right. In our problem, we've got a door. However, we don't know if that door is open or closed. So there's a 60% chance that it is closed and a 40% chance it's open. So if it is open, so it's a 40% chance it's open, and we measured it as being open, that is a 0.9. So we've got a 0.4, 40% chance of it being open, and a 0.9 chance of us measuring it as being open. Alternatively, it might be closed. If it's closed and we've measured it as being open, that's a 0 chance of that. So 0.6 chance of it being open and a 0 chance of actually measuring it as being, 0.6 chance of it being closed and a 0 chance of actually thinking that is an open door when it's closed. So if we multiply all these terms out, we get a value of 0.3. So we've got a 0.3 probability of it being in that location. So I'll just escape that to clean up the PowerPoint slides. So now we want to consider whether it's at position 4. So there's 2 scenarios for that. We can either start in this position and move from there to there to there to there, or we can start in this position and move from there to there to there to there to there. So let's consider this one first. We're starting in this position, so there's a 0.2 chance of being in this position. So there's our 0.2 chance starting here. We next move along. We move along to this position. And in this position, what we've said is our next feature we've detected is these features here. So if this is the next feature we've detected, it means we haven't detected anything at this point. So to not detect a door, then if we look at this door, if the door is open, not detecting it is a 0.05 chance. If the door is closed, not detecting it is a 0.4 chance. So if the door is open and we don't connect, so 0.4 chance of it being open, not detecting it is 0.05. If the door is closed, which is 0.6 chance, not detecting it is 0.4. We've also not detected the wall on the right hand side, so we haven't detected anything on this side, and therefore having a wall detecting no features is 0.7. So we've got 0.7 in here. We move along again. We haven't detected anything here, so we have got a 0.7 chance of not detecting anything there and there. What the example in the book works is as is if there's nothing there, it just assumes it's a probability of 1. So we'll neglect that for now, but technically speaking, you could put a 0.7 term in there. And then when you move to this position here, this is where we think we are. We've got an open hallway on the left. So open hallway, measure open hallway is 0.9. So we've got a 0.9 in here. And on the other side, we have got an open hallway here. But what we think it is an open door. So we've got an open door. We've got an open hallway. We've got an open hallway here. We think it's an open door, and therefore the chance of that happening is 0.1. So the chance of that happening is 0.1. So we can multiply all that together, and we get this value here. However, that's only one chance. So again, I'll just clean this up. That is only one possibility of being in that position. The other scenario is we start from this position and move across here. So we do the same calculation again. We start here, so there's a 1 chance of starting in that position. So 1 there. In this case, we're now in position 2. We haven't detected anything, so we haven't detected an open hallway on the left or door on the right. So not detecting an open hallway is 0.001, and not detecting an open door are these two factors. So not detecting an open hallway here, not detecting a door, depending on whether it's open or closed, is here. And then again, we continue through the problem, not detecting anything at these points, which is going to be the same as our previous case. So these terms, it's the same scenario as these terms here. So it's the same argument. So the probability of going from position 1-2 to position 4 is this calculation, which gives us this value here. So the total chance of being at position 4 is this at this, which is this value. So if we work out in terms of probabilities, the probability of being in position 2 is our 0.3 over the sum of all the probabilities. And that gives us a 99% chance of being at 0.2. Being at position 4, sorry, that should be position 4 there. So being at position 4, that was 0.003 chance over the total probability, so that is 0.1%. 1%. So it's 100 times more likely we're at position 2 compared to position 4 based on them sensor readings. Now bear in mind that was a simplified version of the problem. In reality, what we do is we have to consider each of these as a starting point, and then we translate these to every different position and work out the probability of being at every different position in this problem. So the full problem would be to work out every grid square. For this simple example, we've just considered 2 potential locations. But that's the idea of Markov localization, is you consider the probability where you are, you take sensor readings, and then the chance of them sensor readings happening then helps you identify where the robot is. If you pick the robot up and move it somewhere else, because it's always considering every location, then it should be able to correct itself by taking more sensor readings.
What I'd like to finish with is the particle filter. And the particle filter is kind of a combination between the two. What the particle filter does is you start the robot off in a certain position, and what it does is generates a set of random positions given that starting position. The robot then moves, and all these random positions are updated accordingly. So if the robot moves 1 meter forward, all these positions, or all these random positions, will then be moved 1 meter forward. You then take sensor readings on the robot. So the sensor will detect different features, for example. And then what you do is each of these random positions you generated, you consider how well the sensor readings would match given them positions. So those where a position might match the sensor reading, you give a sort of higher priority to compared to other readings. And you put them in order, so you put the best matches essentially on the top of the list and the worst matches at the bottom. Okay. You then take a random selection from this list. Now we say random, but there's more chance of picking something from the top of the list. So there's a higher probability of selecting this position, or one of these random positions, that shows better features or better matches. So what you do is you select several of these particles. So you select a few of them, so they can be selected from anywhere from this list. But as I said, it's more likely you select a position that shows a good match. And from these sets of particles, you generate more random particles. And the particles you generate are in sort of proximity to that parent particle. Okay, so what that has an effect of doing is you potentially have these particles scattered all over the environment, or these estimated positions all over, but as you take sensor readings, then the ones that are showing the better matches these particles or these positions start clumping together, and that shows more likelihood of where the robot is. So you do that, and then once you reach that step, you kind of repeat the process and go back and repeat it again. So there's a nice image of this in Wikipedia. And there's the example is you have your robot, you take, you generate random positions where it might be, the robot moves, you take a reading, and in this case, the reading detects a door. So those particles, or those positions where they're next to a door, there's more likelihood that the robot is in them locations. So then you resample, and there's a better chance of picking points sampled from these more likely locations. So you've started off here with a random scatter. When you've resampled, it's actually preferentially picking points that are located next to a door. So in this case, the robot is likely to be in one of three locations. The robot moves again. We update the positions, so all the positions have moved. And this time the robot is not next to a door. So any position that is not next to the door has got a better likelihood of being selected. Now you can see we've got quite a clump of particles here and quite a clump of particles here. So it's more likely that these particles will get selected and generate the next set of random particles. So now we've narrowed down the probability of where the robot is at to likely to be at these positions. Robot moves again to here. It's next to a door again. Do the same procedure, and we're starting to clump all the particles together into this position here. So by keep generating random particles but biased towards the best matches, and then matching them sort of with the sensor readings, we kind of hone in on where the robot actually is. So in that case, it's similar to the Markov, where we have lots of different positions, but it's not considering every location. It's just sort of randomly generating them. So it's using its positional information to try and do that. So in that respect, it's a little bit like the Kalman filter, but it's got the advantage over the Kalman filter that, as you can see, there's a chance the robot might be here, here, here. It's likely to be here. This is where most of the particles are. But there is a chance that it's in different locations. So if we pick the robot up, move it, and put it down somewhere, so we've kidnapped the robot, the Kalman filter would fail under that scenario, whereas the particle filter, because of this random sampling, will eventually manage to locate itself again and know where it is. So that's a few approaches to how a robot localizes itself. As I said, if you work through the exercises in terms of the Kalman filter and the Markov localization, you'll see how that works a bit better in practice and gives you a bit better feel for it. So what we'll do in the final video, or the final tutorial video of today, is given we've got a map and we know where we are in that map, we'll look to try and plan a route through that map, through the environment.